Should I wait till it comes back?
Oh, yeah.
Oh, there we go. Well, I see a background. There we go. Okay, so yeah, 4:04, good time to start. So thank you everybody for attending. This is a promotion talk for our Jeremy Holt. Jeremy got his PhD from Stony Brook in 2008. And then from there, he went on to Munich for 4 years as a postdoc. And then he came back to the States. He went to the UW's Nuclear Theory Institute and worked there for 3 years before we were able to lure him in I don't know if you remember, but a very competitive search for a nuclear theorist. So luckily we got Jeremy because he's better than his brother. And in the past 5 years, he's already got a PhD student graduated. I counted, I think, 25 papers. So 5 a year, and not dinky papers either, because there's 4 letters, 12 physical review Cs, and a review article. He's received the NSF Early Career Award. I mean, Jeremy's on a great trajectory, and I'm sure we're going to hear wonderful things today about what he's doing. So with that, I'll pass it back to Jeremy.
Okay, thanks a lot, Dan. Hopefully everybody out there in Zoom can hear me okay, and everybody in here.
Yes, and everyone is muted, so you're good to go.
It's not on, but we can hear you just fine.
Okay, I'll just speak loudly because I think maybe that's best to get both audiences the best. Okay, so thank you, Dan, for that nice introduction. Good afternoon to everybody. So today what I want to do is motivate neutron stars as an exciting frontier in nuclear physics research. Neutron stars contain matter that's really unlike anything we can directly create and study in the laboratory. And therefore, I think they're sort of offer some unique opportunities to constrain our models of the strong force at low energies. So in this talk, I'll basically be describing some recent and upcoming observational campaigns of neutron stars, as well as the nuclear microphysics that goes into modeling their structure, phases, and dynamics. I really think we're just at the beginning of what's going to be a golden era in neutron star physics. So here I have some highlights just from the past 5 years. In particular, in 2017, we measured the first gravitational waves from a binary neutron star merger. 2 years later, in 2019, we saw a black hole merging with some mystery object that was much heavier than any known neutron star and much lighter than any known black hole. So sort of an intriguing object. Unfortunately, we don't really know what it was. In 2020, we measured the heaviest known neutron star. It's about 2.1 times the mass of our sun. 2019, we performed the first simultaneous mass radius measurement of an isolated neutron star. And then in 2021, we performed the first radius measurement of a very massive neutron star, 2 solar masses. So these are all of the kind of observation of neutron stars that are going on. And what I do is I develop theoretical tools that hopefully will allow us to propagate those observations as into constraints on our theories of strongly interacting matter. There's also new rare isotope beam facilities coming online, whose one of their major goals is to create and study neutron-rich nuclei and look for connections to neutron star properties. So to begin, I just want to consider a really simple thought experiment. So just take any form of matter, right? It could be carbon, iron, or a bottle of Coke, and just compress it to ultra high densities. So it turns out that something universal happens. So namely, once you reach about 1 billion grams per cubic centimeter, it becomes energetically favorable to fuse electrons and protons into neutrons. And once you reach nuclear saturation density, so normal nuclear densities shown here in this blue dashed line, you see you can actually convert an enormous number of electrons and protons into neutrons, right? So this neutronization is just an inevitable conclusion of the existence of ultra dense matter. So, there's still an open question. What happens if you go to, 2, 3, 4 times normal nuclear densities? It's possible that you can then start fusing normal protons and neutrons into strange quark baryons, like lambdas and sigmas. But this actually depends on very detailed properties of nucleon-nucleon and nucleon-hyperon interactions. And right now, we just don't know if that kind of process is like robust. So these, matter under these conditions is actually naturally created at the late stage of stellar evolution, massive stars. So those stars that are greater than 8 solar masses, they fuse inert iron in the core. That iron builds up and eventually undergoes gravitational collapse. So interestingly, you never have like prompt black hole formation. Instead, that collapsing inner core of the star always sort of stops at normal nuclear densities, which is 10 to the 14th grams per cubic centimeter. The collapsing material then rebounds against all of this infalling stellar matter from the outside part of the star, and very often creating a supernova explosion. What remains behind, though, of that initial collapse is basically an object that has the size of a large asteroid, but it's 100 trillion times the mass. Right, so this really is like the fate of matter right before it collapses into a black hole. In fact, if you look at the short shield radius, it's just half the radius of the neutron star. So we want to understand the properties of this sort of exotic state of matter. Well, what do we know about neutron star structures? Some things are pretty certain. So first of all, even though neutron stars are born hot, they're about 1 million degrees Kelvin. They're actually very cold in the sense that this thermal energy is just tiny compared to the quantum mechanical degeneracy energy. Right, and so we can basically understand the structure of neutron stars just by finding the ground state by minimizing the energy. When we minimize the energy, we find out that the outer parts of a neutron star is actually a solid crust of neutron-rich nuclei. Eventually, there's just so many neutrons in those nuclei that they begin to drip out and they form a superfluid of neutrons in this background lattice of nuclei. After about 1 kilometer, you can see the whole crust just dissolves. And then you have a sea of interacting protons, neutrons, and electrons primarily as the leptons. So that's where our knowledge starts to break down, because really we don't have any way to study such neutron-rich material in the lab. And so we have a lot of uncertainty still, even in this outer core. So we know the composition, but we don't really know the pressure. That's determined by detailed features of the strong interaction. And after all, it's the pressure that we need to solve for the structure of the star, just using the hydrodynamic stability equations from general relativity. So, if you have a model for the pressure as a function of the energy density, then you can determine the radius of a neutron star given its mass, the maximum neutron star mass before it collapses to a black hole. And there's just a unique relationship between the pressure as a function of energy and this mass radius relationship. So we actually think that pretty much all neutron stars in nature lie on a single unique curve with small deviations due to like rotation, magnetic fields, things like that. What's really exciting though is what could happen in the innermost core of a neutron star. Kind of already mentioned that you could form strange baryons that are stable. You also have deconfined quarks. You can have Bose-Einstein condensates of negatively charged mesons, the pions and the kaons. So there's lots of exciting stuff that could happen, but whether or not they do exist actually depends on very detailed properties of the strong interaction that we just don't understand well enough at the moment. All right, so here's just one example. If you try to use our best models of how nucleons interact with hyperons, say the lambda particle, then what you would find naively, this dashed line, the chemical potential for the lambda eventually becomes smaller than the chemical potential for the neutron, which means that it's favorable to convert neutrons into lambdas. But if you then include this higher order effect with 3 body forces, which kind of account for polarization of baryons, then you see that can actually delay the onset of these interesting lambda degrees of freedom, like essentially indefinitely. Like the lambda, once you include these 3 body forces, has a higher chemical potential than the neutron always. So, unfortunately, details matter when it comes to calculating properties of neutron stars and the strong interaction, and there's just a lot of unknowns. But what we can think about is what would be the, some of the observational footprints of this type of exotic material. So it turns out that very generically, when you create this exotica, you're converting like neutrons and protons that have a high kinetic energy into rest mass energy. Right? So when you convert kinetic energy into rest mass energy, you reduce the pressure, and that'll lead to smaller stars. If there's less pressure, then they'll have smaller radii, and they'll also have smaller maximum masses. So that's kind of one thing that we can at least use qualitatively to infer whether or not these exotic states of matter exist. So let's actually look at what the state of the art for neutron star observations is at the moment. This is just a distribution of the well-measured neutron star masses in the galaxy. Typically, they occur in binary systems because then we can, use like the delay of radio waves from these pulsating objects to measure the mass of the object. So the first thing to notice is that there's a pretty large peak around about 1.4 times the mass of our sun. So lots of neutron stars, that mass. And then really there's this long tail in the distribution. And we just don't know how far that goes, what the maximum neutron star mass is. After all, that's one of the indications for whether exotic matter can exist in neutron stars. So it turns out that all of these neutron stars with masses more than about 1.6 solar masses, these were all just discovered within the last 10 years, right? So we really don't know where this distribution ends. Back in 2010, you saw already this one observation of approximately 2 solar mass neutron star ruled out a lot of different models of strongly interacting matter in neutron stars. Right, so especially this green strange quark matter, this magenta nucleons plus exotic, a lot of those just can't support such massive neutron stars because you've basically converted kinetic energy into rest mass energy. I also kind of like this figure because it shows what the sort of the state of the art was back 10 years ago. Notice that there's lots of different models, and these kind of constraints are basically just binary. Either you throw out the model or it survives. And so one of the things I wasn't really satisfied with at this time is I didn't really like that binary outcome. I wanted to develop some statistical tools that would actually not just rule out equations of state, but actually use basically just develop a whole class of models so that we can propagate those kind of constraints onto constraints on our nuclear force. So the question is, is there some way that we could actually probe the maximum neutron star mass some other way than just by randomly searching in space for the largest neutron star mass? And actually there is. So notice there's lots of these 1.4 solar mass neutron stars out there. What if we just took 2 of them, put them together, and see if what's left over is stable? Right? Nature actually does that for us in neutron star mergers. So one of the things that we look at when 2 neutron stars merge is basically the gravitational wave signal coming from this post-merger phase. Right? What's left over has about 2 times the mass of a regular neutron star. And depending on how long it survives, that can tell us what the maximum neutron star mass is. We're also interested in just this in-spiral phase. So let me see if this pointer works. Yeah, so here you can see that just a few milliseconds before 2 neutron stars gravitationally merge, they begin to deform. And those deformations leave an imprint on the gravitational wave signal, which we can use to extract a property of neutron stars, which is just how deformable it is. So that's called the tidal deformability, lambda. And it basically just measures, it's just a proportionality constant between this tidal gravitational field and the induced quadrupole moment of the neutron star. So that's something that we can also extract from neutron star mergers. we really only have one high quality neutron star merger observation, and that's gravitational wave 170817. What they found is that the equation of state is relatively soft, right? And by that, the deformability is kind of small. Right, so they were able to find that just by looking at the late in spiral gravitational wave signal. Unfortunately, right now the detectors aren't sensitive enough to pick up the post-merger gravitational wave signal. But if they do, that'll give us lots of really interesting physics insights. So also just from this small deformabilities of the neutron stars, which kind of tells us that the radii consequently also have to be small, we're able to get this constraint on the radius of a 1.4 solar mass neutron star. Got to be less than about 13.6 kilometers. However, we were able to get a constraint on the maximum neutron star mass from the electromagnetic counterpart to this gravitational wave merger event, right? And so just the color of the ejected material, the velocity with which it comes out, that all depends on the basically how long the remnant survives. And all of the simulations pointed to pretty much the same conclusion, that in order to explain the electromagnetic properties of this gravitational wave event, the maximum neutron star mass can only be between about 2.2 and 2.3 solar masses. Okay, so I also want to say some recent efforts to directly measure neutron star radii. Right? We saw that mergers can give us some way to infer the maximum radius, but there's also an X-ray telescope, NICER, that's devoted its primary mission is to measure the radii of isolated neutron stars. And this is kind of, I mean, if you think about it, it's kind of crazy because these neutron stars are about 10 to the 16th kilometers away, and you want to measure the radius of that object to within about 1 kilometer. We can do that basically just by tracking these hot spots on a rotating neutron star. It's created by the strong magnetic fields and the magnetic poles. So by tracking the hot spots really through their full 2 pi phase, because these objects are so compact that they warp space-time, and you can measure these hot spots through the full rotational period. What they were able to do is by measuring spectral and temporal features of these hotspots, can model the X-ray spectrum seen. And what they found was the mass of this object, pulsar J0030, was 1.34 solar masses, and the radius was about 12.7 kilometers. All right, so you just have a single neutron star sitting there 10 to the 16th kilometers away, rotating really fast, and we're able to extract the radius to within about 10%. So that's another really crucial constraint that's come online just in the last couple of years. Finally, there's always been this possibility, it's never been realized, but there's always been this possibility to measure the moment of inertia of a neutron star. Right, there's this one particular binary neutron star system that's really highly evolved. And so general relativistic effects are large. One of those general relativistic effects is a spin orbit contribution to the precession of basically the semi-major axis of this ellipse, right? This binary, as they're circling, it precesses, and there's a very small contribution due to the high spin of pulsar J0737A. So if we can measure the spin through this general relativistic correction, we know the angular frequency just from pulsar timing, then we can extract the moment of inertia. Right, and that'll give us an additional constraint on dense matter. So that's kind of the state of the art of neutron star observations. I think there's really lots of exciting things going on. But as a theorist, we want to model neutron stars and compare against these observations. So now I'm going to describe the theoretical tools that I use to calculate neutron star properties. Just want to remind you that like the challenge that all of us in nuclear physics face is the strong interaction. And there are really only a few regimes where we have controlled theoretical methods to actually perform calculations with controlled uncertainties. So of course, at very high energies, we have asymptotic freedom. The coupling constant is small, and so we can perform calculations there. Unfortunately, this is much higher than any energy scale in neutron stars. So it doesn't help us studying neutron stars. Lattice QCD, basically we can discretize space-time and exactly solve for quark-gluon dynamics, but this only works at low densities and high temperatures. Again, can't use this to study neutron star properties. Really our only hope, I think, is these low energy effective field theories of the strong interaction. So the basic idea is, we can take the fundamental theory, the strong interaction, which is quarks and gluons, and we can write down an effective field theory of the actual relevant degrees of freedom at low energies, which is pions and nucleons. Okay, so we actually in nuclear physics we owe a lot to Steven Weinberg, who came up with the idea of effective field theories and first applied it to constructing nuclear forces. Basically, you can write down every single term in the Lagrangian that's consistent with QCD and its symmetries, but then you need some way of organizing all of these different terms. And we can do that by taking advantage of this natural separation energy scales. The pion mass is comparable to nucleon momenta, but these are much smaller than the next most important mesons for the nuclear force, right? The rhos and the omegas. Also, pions are weakly coupled, and so that gives us an organizational scheme when treating all of this infinite number of terms that are just consistent with QCD symmetries. Right, so we can actually systematically build up the nuclear force, powers of this low energy scale divided by the high energy scale. And don't worry about any of these diagrams. Basically, the solid lines, though, are nucleons interacting through the exchange of these dashed lines, which are pions. What the theory doesn't tell us what happens at very short distance scales. So this is real, after all, this is just a low energy effective field theory. So it doesn't tell us what's going on, very high energies. So those we just have to parameterize with a large number of constants, 25 to 30 at the most. And we fit those just to the properties of nucleon and three body systems. But then you have a model of the nuclear force that you can then go and try to calculate for the structure of neutron stars. So what do we want to calculate? Basically the ground state energy, right? Because these neutron stars are cold. So what we can do is we can calculate the ground state energy, basically just energy per particle as a function of the density. Here I just want to highlight that this black curve would be the energy density of non-interacting neutrons. When you turn on the nuclear force, then you get this blue curve. Of course, the nuclear force is attractive, so you get lower energy. And then if you start converting like half of the neutrons into protons, then you have self-bound systems like finite nuclei down here. Okay, so nuclear experiments are really just probing the equation of state in this pretty limited region. And what we need is really the full equation of state at arbitrary proton-neutron fraction out to something like 5 to 10 times normal nuclear densities. So it's a major challenge. Here I just want to highlight some of the important parameters here in the equation of state. There's this isospin asymmetry energy, which is just the difference between isospin symmetric nuclear matter and pure neutron matter. And then we have this slope parameter, L. And these empirical parameters are actually really useful because they allow us to connect properties of nuclei to the equation of state. All right, so just one example is the neutron skin thickness of lead-208. So of course, so lead has proton distribution, which is pretty well understood just from electron scattering experiments, but the neutron distribution is not well known. Since there are so many neutrons, there's a skin, and just depending on what the pressure of the neutrons are in the skin of lead-208, that's strongly correlated with the pressure in neutron star matter. right? So this gives us a constraint. The neutron skin thickness of lead-208 gives us a strong constraint on this symmetry energy slope parameter L, right, which is actually closely tied with properties of neutron stars. We can also look at how polarizable a nucleus is in a background oscillating electric field. Because after all, it's this neutron-proton asymmetry energy which provides the restoring force to any opposing movement between the protons and the neutrons. So, you know, I'm actually building some models with my brother and collaborators where we're calculating exactly the electric dipole polarizability of nucleons and relating those to models that just involve these nuclear matter empirical parameters for the equation of state. That's just two ways that we can try to connect nuclei to neutron stars. Okay, so what we did a few years ago is we basically took all of our different models from this low energy effective field theory of nuclear forces called chiral effective field theory. And we basically, I mean, the nice thing about the model is that there are lots of different ways that you can sort of tune things to quantify the uncertainties. So these were our uncertainty bands for the symmetric nuclear matter and pure neutron matter equation of state just from theoretical modeling. Then when we built in some constraints from the properties of medium mass and heavy nuclei, like I was kind of just discussing the last few slides, then our probability distributions on the equation of state were greatly reduced. You can see the resulting distributions here. And then once you have this model, you can then calculate the structure of neutron stars. So this is what I did with my postdoc, Young-Won Lim. He's now a professor in South Korea. So he came up with this big distribution of curves just based on what we thought was the best nuclear physics modeling at the time, right? So you have this, you know, the mass is a function of the radius. You see the radius of a 1.4 solar mass neutron star. It's about between 10 and 13 kilometers, right? This doesn't build in any kind of observational constraints. It's just from nuclear physics. Right, this gives us the probability distribution for the radius of a 1.4 solar mass neutron star. Seems to peak right at about 12 kilometers. Notice that agreed pretty well with these nicer observations, which gave neutron star radii about 12.7. Are the maximum mass neutron star that came out of our calculations was between, you know, about 1.8 and 2.3 solar masses. You know, it's kind of interesting because this just so happened to agree pretty well with the analysis of the neutron star merger event, which also gave a pretty similar range for the maximum neutron star mass. Our models, though, only include nucleonic degrees of freedom. So what this might be telling us is that, you know, there are kind of some hints that there's nothing super exotic going on in the core of a neutron star. Our minimal model with just nucleons and electrons seems to give a pretty similar maximum neutron star mass as is observed from neutron star mergers. And there's this, I think there's a nice consensus growing in the community what the radius of a 1.4 solar mass neutron star is. So this, in blue, this was our prediction back in 2018. We have some updated results from 2021. But basically, a lot of different analyses are giving the same picture. The radius is about 12 kilometers plus or minus, you know, 1.1. And so you see, if we then take the nicer observations of pulsar J0030, it doesn't really change our distribution too much. We just get rid of the very the very, you know, most compressible equations of state. So what we find is that right now, I think theoretical calculations and observations are on the same footing, and they're pretty consistent with one another. We also calculated the tidal deformability of these two neutron stars in this merger event. And it agreed very well with the analysis of LIGO and collaborators. Again, in fact, our modeling was a little bit more constraining than what comes out just from direct observation. Right, so LIGO, they basically said anything below about 800 in this binary tidal deformability parameter, but we have between about 200 and 600. Okay, so again, those just our best nuclear physics models agree pretty well with current neutron star observations. There was this one interesting case, it was reported just last year. So there was a 23 solar mass black hole that merged with this 2.6 solar mass mystery object. Right, as I showed before, 2.6 is actually a larger mass than a lot of theoretical models predict, and it's much larger than any observed neutron star mass. But no black hole has ever been observed that small. Basically about 4 solar masses is the lightest black hole. So this really was a mystery object. Unfortunately, it was just swallowed whole by this black hole. And so we'll never see it again, and we'll never know what it was. But it's kind of intriguing nonetheless to think about the consequences either way, if this had been a black hole or a neutron star. And so that was something that I did with postdoc Yunhwan Lim, as well as 2 statistics professors here at Texas A&M. We basically took all of the observational constraints from NICER, from this first neutron star, double neutron star merger event, 1708-17. And we just asked ourselves, is it possible to support such high mass neutron stars? And the conclusion is that it was, we could build up the models, but what it required is a profound change in our nuclear modeling at about 2.5 times normal nuclear densities. Right, so something would have to happen at about 2.5 times normal nuclear densities for this to even have been a neutron star. We also showed that there'd be a strong correlation between this maximum neutron star mass and the radius of heavy neutron stars. So that's something that we can also test with future observations. We also calculated, this is work done with Robert Stahulek, he was a REU student at the time, but now he's a PhD student here at Texas A&M. We made a theoretical prediction for the moment of inertia of this one neutron star in the binary system. So this is a pure prediction. There's absolutely no observational constraints on this quantity, but we think that the moment of inertia will be between about 1.2 and 1.5 times 10 to the 45 grams per centimeter squared. And that's compared to some of the other, so this is our blue prediction, and then these are 3 other theoretical predictions for the moment of inertia of this one neutron star. So hopefully within the next decade or so, this will actually be measured and we can further test our models. Interestingly, there are actually very strong correlations between these bulk properties of neutron stars. The radius, the tidal deformability, the moment of inertia. This shows the correlation between the moment of inertia and the radius of the star. Right, it's pretty tight. So a very strong or a very precise measurement of either of those quantities would be very strongly constraining on the others. Same with the correlation between the moment of inertia and the tidal deformability. That's just almost a line, right, with no uncertainty. In fact, there's some it's a celebrated universal feature of these two neutron star properties. There's a prediction that basically there has to be a 1-to-1 correspondence between these 2 quantities. So you can see, we've got these 3 different properties, and presumably all of these different observational techniques have different systematic errors. So it's really nice to start, confronting them against each other and with our nuclear physics models. So that's really all I wanted to say about bulk neutron star properties. I think I'll say a little bit at the end about some of the upcoming observational campaigns. But now I just want to turn and talk in the next 10 minutes or so about some of the dynamical properties of neutron stars and neutron star mergers. So one thing, we expect neutron star mergers to be the source of about half of the elements beyond iron, right? So normal stellar burning, Nucleosynthesis stops right about here at iron. And then half of the stable elements are created in some kind of astronomical event that involves a huge flux of free neutrons on seed nuclei, which get captured and then they radioactively decay back to stability. Neutron star mergers is one of the prime candidate sites for the R process. However, there really are large theoretical uncertainties in these neutron capture rates that strongly influence the late time evolution of these R process sites. So one thing that I did with Taylor Whitehead, my student, so he just graduated this year, now he's at Michigan State University. We developed some new nuclear reaction theory codes that are publicly available. Anybody can use them, and they should have a high quality in this really neutron-rich region of the nuclear chart. So of course, we can only benchmark to existing nuclear reaction data, but our predictions for a wide range of isotopes is shown in blue compared to experimental data seems to be pretty good. And we have no reason to think that these models would be significantly worse out away from stability. We're also really interested in the role of neutrinos in both supernovae and neutron star mergers, right? The neutrino winds actually cause a lot of the material to be expelled from neutron star mergers. It governs the composition of the objective matter, its velocity. So we need to better understand how neutrinos are interacting in a hot and dense environment. Because in such a dense environment, nuclear correlations are actually important. So this is work done by Eungyung Shin, who's a PhD student in my group. Basically, she's looking at so these mean field corrections to neutrons and protons and neutrino absorption in a medium. So those are pretty well known, but what's very poorly known are the role of these vertex corrections to neutrino absorption. These are just really difficult to calculate. But anyway, we've devised some tools to actually calculate those kinds of diagrams, resum them to all orders. And we find out that they're just as important as these mean field effects, which sometimes simulations just include the mean fields without the vertex corrections. And we think that's going to need to be modified in the future, just because these vertex corrections are really important. Also, in order to dynamically model a neutron star merger or a supernova explosion, you need the equation of state at finite temperature. What's the pressure when you now ramp up the temperature to, up to 100 MeV, right? That's sort of the maximum temperature reached in neutron star mergers. That's something like 1 trillion Kelvin, so extraordinarily hot temperatures. So we actually can't calculate such high temperatures in our low energy effective field theory, but we can go up to maybe about half that temperature, and then hopefully we can extrapolate to higher temperatures. In any case, there's really been no, all of these neutron star merger simulations, all of these supernova simulations, they really rely on just simplified models of the nuclear force. So one thing that I've been developing is some tools to construct these big equation of state tables using realistic microphysics, and then put those into the simulations. It just hasn't been done before. It's actually really challenging, just numerically, because you have, in order to construct these equation of state tables, you basically need the pressure as a function of density, the composition, the temperature, across like millions of phase space points. So it's just numerically computationally demanding. So one thing I've been working on is some deep learning tools to more efficiently calculate quantum corrections that go into the calculation of the pressure. I won't get into too many details here. But this was actually work done by an undergraduate computer science major working with me, Pengsheng Wen, who's a PhD student in my group. And we were able to develop some pretty powerful machine learning tools to calculate these complicated integrals basically to an order of magnitude higher precision than state-of-the-art Monte Carlo methods. So this factor of 10 corresponds to a speed up of 100, right? So if our calculation takes 1 million hours. It would have taken competitors 100 million hours. So a big improvement. And we showed that these machine learning models, once you train it on one set of conditions, it can very easily explore all of the neighboring densities, temperatures, and composition. Okay, so that's something else that my group is working on at the moment. Just better inputs to numerical simulations of supernovae and neutron star mergers. Some of the recently funded collaborations I'm involved in are shown here. So MUSES, technically it's not funded yet, but we've basically been told to go ahead and get started from the funding agency. So MUSES stands for Modular Unified Solver of the Equation of State. There's lots of different communities that need the equation of state to understand the dynamics in their systems, such as, of course, supernovae and neutron star mergers, but also relativistic heavy ion collisions, as well as cold neutron stars. The idea is just to develop a centralized place where everybody, we're all developing contributions to the equation of state in certain regions of the phase diagram. And what we're going to do is merge them all together and allow some external user to basically say, well, I want an equation of state that contains strange degrees of freedom, that has chiral effective field theory as the low energy theory. So it's modular. You can, the user can tell you what conditions and what properties of the equation of state they want to include. And hopefully we'll build the framework so that these vastly different communities can all use the same framework to study the equation of state and the impacts on these observables. There's also the NP3M. This was recently funded by the National Science Foundation. Ralph Ropp is also part of this one. So here we want really to develop more coordinated interactions between the nuclear physics community and the astrophysics community doing the simulations, and then also the gravitational wave experts. So it's really an opportunity for postdocs to get training across a wide range of fields. Traditionally, the gravitational wave community has been completely separate from the nuclear physics community, but we need to start building stronger connections and young people who are skilled in all aspects of the important science. So that's the plan of NP3M. So just in the last minute, I want to talk about some upcoming observational campaigns of neutron stars. So NICER, it's been extended to the end of 2022. They think they'll get double the statistics on this one well-measured neutron star mass, J0030. So we should be able to reduce the error bars down to about half a kilometer at 1 sigma. That already would be pretty good. I think that would start constraining my models more significantly. And then next generation X-ray telescopes like EXTP or StrobeX, here you expect to be able to measure the neutron star radius down to precision of 2%. And that would be just enormously constraining on nuclear physics models. And so what I want to do is develop techniques that would allow us to propagate those constraints back to nuclear physics. Next generation gravitational wave detectors are in the works. We're really just at the birth of this field, shown here in 2021. But over the late 2020s into the 2030s, we're actually, as long as these get funded, which I don't see any reason why some of these wouldn't, we're going to start measuring up to tens or even hundreds of thousands of neutron star mergers per year, right? And so just with that much statistics, it's going to be enormously constraining on nuclear forces models. Right, so shown in green, this is sort of one of the pillars of these next generation gravitational wave astronomers, or gravitational wave astronomy, just the study of ultra-dense matter in neutron stars. These third generation detectors like the Einstein telescope or Cosmic Explorer get built, they'll be able to see binary black hole mergers basically since the beginning of time, redshift 100, and they'll be able to measure neutron star mergers out to about redshift 10. But again, just huge, it's going to be a big data problem for the gravitational wave astronomers, but it's going to be really exciting time for us in nuclear physics. So that's where I want to end. I just want to say that, really this ultra high density region at the center of a neutron star, to me, that's the most important thing, most exciting, but there's just so many challenges on all fronts for understanding what's going on at high densities. I think there's a lot to do, but there's also a lot of exciting things in the works. So thanks a lot.
Clapping on Zoom as well. Thanks for the nice talk, Jeremy. Hope everybody can hear me. And we'll open it to questions. I guess I don't see any on Zoom, so maybe Reiner, if you want to take over locally.
Okay, that's just, I don't know who had the hand up first.
Oh.
Okay,
Well, while you're doing that, actually, Sue, there's a question. Just unmute and ask, Sue.
Okay. Hi, Jeremy. Let me just show myself. I don't know why. I'm sorry, I don't know why it doesn't zoom, but I'd like to know for your calculation, the calculation you have for neutron star where the mass are above 2 solar mass, what is the central density so that one can gauge whether the matter is relativistic or not?
Oh, the central density is about six times nuclear density, 6 or 7.
6. So do you consider that relativistic?
Well, yeah. So it's relativistic. That within our theoretical framework, there's within this effective field theory treatment, we have relativistic corrections, but we don't have full relativity built into the theory. So there are some attempts to do that, but they're really not making good traction developing covariant chiral effective field theory models. So there are works underway, but I think the non-relativistic models, even though they do suffer from some defects, I think right now they're still the best game in town. That's just my personal opinion.
Thank you.
Mm-hmm. Okay. We have more online, but I don't know if there's anybody.
Alexei Akimov has a question here in the room.
Okay, let's go back and forth.
two related questions. One about the neutron star, which is 2.6, I think, solar masses. So what is conservative error bar of that?
Oh, okay. So Alexei had a question about the 2.6 solar mass neutron star. What are the basically what are the error bars on that? So we actually don't know what it was. That's the thing. So it was either a black hole or a neutron star. We don't know what it was, but we do know very precisely the mass. I don't remember what the actual error was, but it's on the order of like %, very small error bar. So you can extract this pretty reliably from the gravitational wave signal, the mass, the component mass.
Okay, and the second question is, it looks like a lot of observation are focused on one star. Why one kind of star can make a deep conclusion out of one?
Yeah, okay, so just keep in mind that these are like hundreds of parsecs away, and they have a radius of, or they have a diameter of 25 kilometers. So they're extraordinarily difficult to observe, and single observations are extraordinarily special. So maybe you're talking about the one radius measurement.
Yes.
So NICER just came online in 2017. So it's an X-ray telescope on the International Space Station. Just came online in 2017. This was the first target. Of course, they are moving on to other targets, but it takes a while to build up the statistics just because these objects are so far away. It's so difficult to accumulate the needed statistics to make a precise radius measurement. Alan? Yeah, Alan, there's a question here in the audience.
Okay, my question is, earlier in your talk, you showed, maybe in the first third, a figure of the energy versus the density from theory, and then a posterior based on experimental constraints. And it looked like you narrowed both the symmetric nuclear matter distribution everywhere, but the neutron matter narrowed, but only at below nuclear saturation density. Yes, this one. So I wonder what experimental constraints went into the plot on the right and why you got so narrow below saturation density but not near it. If you're doing masses and giant resonances, I would expect more constrained saturation. So you have scattering data in here, you have nuclear reactions as well.
Okay, so for those of you on Zoom, the question was, so in going from the this prior probability distribution to the posterior probability distribution, why did we see such a strong decrease in the symmetric nuclear matter uncertainties, but not such strong constraints on the neutron matter properties? So I mean, it's really because we understand very well the binding energies of nuclei, so the saturation energy, the saturation density. So we basically know this to 1 MeV, right, up or down, and we know the saturation density, to within 0.01 inverse cubic Fermi. So it's really just because we know the properties of normal nuclei, symmetric nuclei, so much better than the properties of pure neutron matter. So to constrain this, we basically just use the constraints on the symmetry energy. And that was a global analysis of lots of different experiments. So
my question is more for the neutron matter.
Oh,
why, do you think you know it so well at the very low densities?
Yes.
Why?
Oh, why?
It's already the prior, right?
Yeah, I mean, already in the prior, we have very small uncertainties in the neutron matter equation of state. And that's basically because our effective field theory, we think that it works very well in this regime, right? Low density neutron matter has a pretty small Fermi momentum. And so if you're thinking of an expansion in powers of the characteristic momentum scale divided by the chiral symmetry breaking scale, the expansion should be well converged at low densities for neutron matter. Nuclear matter has problems with clustering and things. There's non-perturbative features here, but in neutron matter, we actually think that our effective field theory is what's driving the low uncertainties there. Yeah, there's one more from the audience, Joe.
Oh, we do have them on Zoom too. Maybe.
Just talking.
Yeah, how about
I just muted the laptop, so I was just trying to see what's happening because I can see people leaving. So I'm just confused if it's over or not. Oh, fuck.
Yes.
So I don't know. I guess Ralph is the next one in line.
Okay, yeah. Let's do
Thank
that.
you. So yeah, I have a question that is turns out to be related to also what Zui was saying. So I was surprised that you actually have densities of 6 times nuclear matter in your calculation, where I don't think your theory is it's very reliable. In fact, at that time, I would definitely expect Colloquium degrees of freedom to kick in. So, so I have 2 questions. So first of all, are you extrapolating indeed your calculations with this effective field theory to those densities? And 2, and that was my main question. You mentioned that the little black hole, which was swallowed by the big one, where you see where there's some evidence that something maybe happened 2.5 times nuclear matter density. And I think if that were true, that would really be great, because we know that at finite temperature, this is precisely the kind of energy density where things start to happen toward the phase transition into a Colloquium plasma.
Yeah, so to your first point, I absolutely agree. And, if in our papers, we made strong caveats about, the fact that we actually only trust our models about twice normal nuclear densities. But nevertheless, we just extrapolate. We extrapolate well, we don't actually do the calculations at high density. We parameterize the low density equation of state and then extrapolate that parameterization. But you're absolutely right. We have no reason to trust our theoretical modeling beyond twice saturation density. But for us, that was like the minimal model, right? Just assume that the same physics is sort of applying at higher densities and just see what occurs, right? We have no reason to trust it, but we can extrapolate it with caveats. And I think the kind of interesting thing that came out is that we can't produce anything more than about 2.2 solar masses, which is the maximum mass inferred from gravitational wave events. So,
but is that part of your error analysis that basically arbitrary things could happen more or less at those high densities?
no, so we actually took, we accounted for that problem in the follow-up paper. So I don't, so if you look at, yeah, so when we studied this potential of this 2.6 solar mass object as being a neutron star, you know, we absolutely had to consider a wider range of nuclear physics models at high density. So here again, we took sort of the simplest approach. We said there's a transition density at which you basically reach the maximally stiff equation of state beyond that transition density. And so that allows you to generate high mass neutron stars. And it can place some rigorous constraints because it's basically the most extreme model for what can occur after like a phase transition. So yeah, we had to extend our modeling to include more complicated features at high densities. And you know, this is a work in progress. You know, I would love to work with people developing quark models such as yourself to build better models for what's going on at high densities. It just takes time to do that kind of analysis.
Thanks.
Joe.
So Jeremy, if you think about less exotic neutron matter and potential observation of a tetraneutron, for example, what about neutron clusters? Neutron pecks and neutron, what sort of role could they play?
That could be pretty important because okay, so the question is what could like clusters, so there's no 2 neutron bound state, but there have been suggestions in the literature that there could be 3 neutron bound states, 4 neutron bound states. And the question from Joe is, what could be the implications for like tetraneutron, stable tetraneutrons on the dense matter equation of state. So I think that if we could measure the binding energy of tetraneutron, I think that'd be extremely interesting, right? Because what we don't really understand, one of the largest uncertainties is 3 neutron forces in our models. So I think a 4-body bound state between or among neutrons could be potentially very constraining on the 3 neutron force that goes into all of these calculations.
Would it have effects on the neutrino opacities and the supernova? Nuclear synthesis and such things?
I probably not, because there the matter is, well, no, I mean, there the matter I'm sure is too hot. I'm sure any kind of, I'm guessing tetraneutrons would just be dissolved. And yeah, like the neutrino propagation in the hot matter, that's primarily governed by 2-body correlations. There's a question from Alexei.
Small one, so I'm kind of back to the 2.6 solar mass treatment report. So why can we exclude the fact that it was a binary? It was 1.3 solar mass stars.
Oh, for sure, yeah. So the black hole had a mass of like 23 solar masses.
Yeah, but like let's assume that it has binary neutrons.
So a black hole and a binary neutron star. Yeah, I mean, you can't have those kinds of like triple systems. That would have shown up in the gravitational way.
Would it? Because,
well, let's see. Yeah, it would have. It would have. I'm almost sure you would have been able to see it. So, so you're sort of assuming that the 2 neutrons are not evolved. But if they were, yeah, but once they get close to the black hole, I think one of them would probably be ejected dynamically. I do not know. I don't know. Yeah. So the question was, yeah, could this 2.6 solar mass object have been 2 neutron stars in a binary in rotation around a big black hole? I I'll think about it some more, but I suspect we could have disentangled that in the signal, but I'm not 100% sure. Anything else? Any other questions on Zoom?
No, Vlad had to go, I think, and I don't see any other hands up. So, and none there. So if not, let's thank Jeremy again for a great talk and
Thank you.
good questions. And okay, well, yeah, have a good night, everybody. And thanks again, Jeremy.
Thank you.
Jeremy, I had a comment. Have you seen the Radii et al. 2021 paper on this really massive?
Yeah, with the new radius measurement. Yeah. So I think we're still working to build that into our calculations, the posterior distributions. So yeah, that was another really good observation. Yep.
Yeah, there's I guess a companion paper from Reich makers. I don't know how to pronounce that Dutch name, but where they have the constraints on the equation of state.
Yeah, right, exactly. So I think Anna Watts is kind of part of both of the collaborations, and so yeah, she's the connection there. Yeah, they get all this data before we do, so
right.
They're sort of cheating, but yeah. We'll end up doing a similar analysis. I'm sure we'll find pretty similar conclusions. Yeah.
Very exciting. Yeah. Yeah, I don't know whether the timing works for this 2.6 solar mass object to have been two neutron stars that merged, to produce a black hole a long time ago.
Oh,
and then for that black hole to inspiral,
yeah, right, exactly. So that sounds like that could be a very reasonable possibility. I think Alexei was thinking there were actually two neutron stars rotating, in a.
Yeah, that